Very good. So welcome back to our course in cyber physical systems. Today we're going to continue covering chapter 6 on systems engineering and software engineering. And we ended up, or yesterday we finished covering some preliminary information on systems engineering. And today we're going to start discussing what are the design challenges in the representation of cyber physical systems that makes the techniques and discipline of systems engineering so attractive to be able to manage the design of these complex systems. So we know, by now, we have discussed many times that cyber physical systems are complex systems that are tightly integrated with their physical environment, and they're also connected, presenting issues of security as well. So in a nutshell, that's kind of the definition of cyber physical systems. Now, because the heterogeneous nature of these complex systems, it is natural that many engineering disciplines are going to have to be involved. And beyond different engineering disciplines, you have to bring in domain experts, which is one layer removed from the engineering design core. For example, if you are working on a medical equipment, a domain expert would be a physician. That's not an engineering function, but you need that because you don't know enough about that external environment, which is the physiology of perhaps a human that you're going to be interfacing with. So those are the domain experts. So you have to try to bring in not only multiple engineering disciplines, but also domain experts from outside engineering. So people have started to look at this problem, see how can we formally define some methods. And there are some techniques that are axiomatic in nature that have tried to mathematize the mapping of what to how, which is a big part of systems engineering, is how do you separate the what from the how and start with very clear what. What is it that the product needs to do? Okay? And so on. Without worrying about how it's going to happen, you just want to have a very clear vision of what this product has to do to serve its purpose, its mission in the marketplace. And then systems engineering takes you through a process of transforming those whats into how are you going to deliver the whats by engineering design in a way that you optimize not only the execution of it in terms of budget and timing, but also optimizing certain technical metrics. So you know that you have an efficiently designed product that can be sold competitively. So that is a big part of modeling and representing cyber physical systems within the systems engineering framework. Now, as we start our path through this system engineering sort of journey, starting with the understanding the what are the things that we need to do there? Well, it really starts with a discovery process. So normally it's well known, for example, in legal enterprises, the art of discovery. If there is litigation, there is a phase of discovery. And that's when each legal team tries to find out as much as possible because they have to argue later in court. Well, we use the same word, discovery. Finding out as much as you can what are the perspectives of your customers so that you can arrive to that clear vision of the requirements of what the product needs to do. And then, if you do that, We're not talking about just what does the product need to do when I get a few prototypes of them. Really, we're thinking about the whole life cycle, as we mentioned yesterday. It's not just about design, it's about what needs to happen to manufacture this. And it may be that your customer doesn't know enough, doesn't have the technical acumen to be able to articulate that, but you have to start knowing as much as your customer knows to extract that and extrapolate, and they're going to be relying on your expertise to do that extrapolation, which again is not a trivial thing to do every time you're extrapolating. So you have to continue that journey through the life cycle. Design and development, what do we need from a manufacturability perspective, and then beyond that, what do we need after deployment into the marketplace, into the field. So then we're talking about reliability measures, maintainability, things like that are way downstream, but the things that you do during the design on this house are going to affect things that are, or maybe many months away. And finally, your customer, for the life cycle of her product, may have a need for disposability considerations, and you may also have to bring that into the care-abouts of the design. So as we go through these stages, the best thing, rather than pose a lot of narrative, the best thing at this point, as we go through these stages, is to pose the different stages as questions that are yielded by the execution of these processes. So I find that when people give you a narrative, they are most of the time discussing and coming at it from a position of comfort. They're talking about what they know about normally. When you are asking questions, you are always coming from a position of discomfort because you don't know. That's why you're asking questions. And because from a cognitive perspective, you're coming from that position, coming up with relevant and good questions, it is difficult. I think you guys know that. It is difficult. So what I have here for each of these activities is a set of questions that may be yielded from the activities themselves. So let's start with the first one. We want a good statement of the problem. So what are the questions that this process yields? How doing this in the right way? How can we do this in the right way? How can we state the problem? And all these questions are very open-ended, but these are part of a thought exercise that if you are starting a project and you want to maximize the information that you extract from this discovery process, you go through this thought exercise with your team. The team that is, it may be only you that is in charge of doing that activity. It may be 2 people. It may be a team, whoever. But you must go through this thought process. That is more important, rather than, I'm not asking you to write down the answers to these questions, but to think about it. And there is a lot of power and benefit in just sitting down and thinking about things. That's very valuable. So, as part of the statement of the problem, what happens when we use flow diagrams for the systems engineering part of it? What type of flow diagrams? Decision feedback flow diagrams, UML-based diagrams. What is the best way of expressing this problem. It may be that one representation may be better than another one. How systems engineers should search the customer's environment to find out what customers are planning using the system. So in this case, when we talk about customers, we're talking about the end user, of course. You may be commissioned by someone that wants to sell the product that you develop, but who is the end customer, the end user? Can you see if there is something available what they do now? Can you get a feel for that? So that's another question. What other methods can help you fulfill the requirements to state the problem? Is it a focus group? Is it surveys? Is it a deep conversation with just some key people, influencers, experts in the domain, things like that? How are you going to do requirements validation? Is it going to be helpful? Do you have at this point enough information to do that, or do you push it downstream when you gather more information through subsequent processes? So, questions like that. And this is just on the activity of stating the problem. We have more. Now that if you have a clear view of the problem, you want to investigate alternatives to solve the problem. You're getting closer to transform the what's into how's before you end up with an actual design specification from the system engineering perspective that can be developed. So you have to think about alternatives. So all these activities are at the system engineering level. They're not at the detailed design level by any means. So when you're investigating alternatives, you may have to answer questions like this. How do you make decisions to choose an alternative that satisfy the requirements better than others? What are the metrics? What are the criteria? And how are you going to come up with those? And once you have a product, how does the test, the acceptance, and the validation of the design starts to look? What are the things that you have to put in place for that? What is the most critical criteria? How do you separate criteria into tiers? There are tools for that. Yesterday I mentioned the house of quality approach, which comes from a part of what is called total quality management, which is called quality function deployment. So you may have to think about what tools are you going to use to be able to stratify the different criteria for the different approaches. If you have to do trade-off studies, how do you do those? And how much time you spend on them? What is the return on that investment of doing exhaustive trade-off studies? And then when you have the data from those studies, how do you translate that data and the results into tangible and actionable results that you can put in your design spec? Once you have an idea of the problem and you have conceptualized perhaps different alternatives and done perhaps some trade-off studies, and you have chosen one approach or have narrowed the field of the approaches that can be seriously considered, that's when you want to start modeling. You have to model the system. So you have to perhaps answer questions like this. What is a general model of the system? So that's pretty straightforward. How can you start modeling not only the system, but also the process of requirements gathering from a system engineering perspective? And what are the differences of these models? So these are two types of models. The tools for systems engineering that we have available and are becoming even more available allow for this. For example, we mentioned event-based simulation as part of using that technique to model the system. We mentioned that yesterday, but that's more about modeling the system. How do you model the process of gathering the requirements so you have a way to measure the quality of your requirements gathering process? So we're getting more and more tools to do this. And there are series of tools that have come about into the marketplace, and they have come at it from different backgrounds. For example, Boeing uses a proprietary tool that they have actually toyed with the idea of bringing into the market as a product because it's very good. And that is a more classic system engineering type of approach. And systems engineering has a lot of rooting on the aerospace industry, people like Boeing, NASA, etc. So they have a good tool. And people such as smaller companies, although it got acquired recently, we were using Core in our systems engineering course. That is more of a classic systems engineering approach to the requirements gathering. And they added then more features for the technical simulation of the systems engineering device, emerging and moving from the classic systems engineering background. Your book mentions a tool called Cradle, which also is in that category. So I tried to be in this presentation agnostic to any specific tool, so I'm not going to cover the specifics of any given tool, but I'm mentioning some of the ones that are available. Cradle looks like a pretty good tool if you look at it, and the price is very competitive. You have other tools. IBM, probably the most complex and comprehensive tool, is the Rational suite of systems engineering modeling and requirements gathering modeling. So the Rational suite is huge. By IBM, they come at it from this software engineering background. And then I'm very happy that MATLAB or MathWorks is jumping into the game of systems engineering because they are starting to deploy systems engineering tools, but coming from more of the sort of control, electrical, computer engineering background, because they have things like Stateflow, which is a toolbox that models events. You can do event simulation like the one that we discussed yesterday, but now they are putting more of the requirements on top of that. So each company, they come from their position of experience or strength. But I'm glad, since we have such a profound connection with MathWorks and MATLAB here in our programs, we're switching to that, and I'm glad that they're going that way. So you have to think about all that. Which tools are you going to go about modeling? At some point, you're going to start developing. At some point, you have to actually start doing things. and integrate system components as part of your development. So you have to start thinking about that process, not just the specific components and specifications, but the process of bringing components together. Make versus buy decisions. What are the things that you should be developing in-house as part of the development project, and things that you should be buying off the shelf? There is a trade-off there, not only from a design perspective, but also from an economic perspective and execution perspective. So thinking about what is the most efficient way to bring components together, and also how do you design and manage the interfaces? So we have mentioned that interfaces are a big part of complex system design. Not only the internal interfaces, but also the interfaces to that external environment that cyber-physical systems are tightly coupled with. And also, what kind of system engineering assumptions and comparison tests, studies of process can be said to be successful. So as you think about your processes, what are the best processes? How do you learn about it? And that's why it's important to keep up with what other people are doing, attend conferences, read periodicals, and things of that nature. Then you're going to get eventually to a point in the life cycle where you launch the system. And that activity may yield the following questions. How do you start to launch the system? That's a very fundamental question. What are the things that must happen? What are the preconditions that you have to have in place? What is the infrastructure? When you launch a system, what is the impact of stakeholders and the opportunity for them to comment on proposed changes? So once you start validating that system and you launch it, what is the overall governance process to make sure that stakeholders have an opportunity to comment on changes? And how do you limit that, and you bound that input to a way that is practical or manageable? Actually practical and manageable, because practicality may be subjective. So how do you do that? How do you maintain a body of knowledge of what's being done? So a big problem in industry, because we're all trying to go as fast as possible. That's always the case. You want things as fast as possible. Is documentation, in the sense that tribal knowledge becomes very important. So knowledge that is attributed to one person or to a very specific group of individuals, and if those people are no longer in the project, there can be a catastrophic void of knowledge and continuity. So how do you gather specific information and history to assure continuity of the execution? So we can talk about an engineering notebook of knowledge for a specific system or development, which is an abstraction. We're not talking about an actual notebook. But how do you capture the history of what has been done, so that if people move around and shifts happen in the resources of the project, how do you ensure continuity. And what is the usage mode of this type of data, of this type of engineering notebook? This is something that you cannot automate. Documentation is very, very hard to automate in a way that is useful in the way that we are talking about here. So people have to do this, and people dislike it. So as a system engineering champion trying to foster this type of methodology in your team, how much do you request? And you have to be cognizant of, how much people want to do. So systems engineering, if you ever find yourself in a position in a team where you are trying to foster this type of thinking, you're going to learn that you're going to have to sell it. You're going to get resistance, because human nature is that we want instant gratification, and this is not about instant gratification. This is about investment and delay gratification to get something that works, but people like to start tinkering and putting things together right away. So you have to sell the benefits on the merits, and it does have merits to be sold on. How do you assess performance then when you have something to validate? And before I start, I want to say something more on this part of the engineering notebook. Some industries actually, under regulatory necessity, you have to keep a very detailed sort of engineering notebook, which is called, for example, for medical devices and medical things for FDA approval, there is a need for something called a design history file that has its own format. It's very complex, takes a lot of time. It may be the time that it takes to keep that together, maybe 20% of the overall resources of the project. It is a huge undertaking, but that's, from a regulatory perspective, that's what is required if you want to get FDA approval of something. So that's an example. Going back to the assessment of performance, that activity may yield questions like this. How do you measure the performance of the system? How do you define performance? So you have to think about questions like this. What is the level of convenience of verifying that the system is in compliance with its requirements? So if you are building a Mars rover, well, you cannot go to Mars to test it. So that's an extreme example of inconvenience. So you have to think about that. As we're going to these are activities that are going to happen. This is a key point. These are activities that are going to happen in the future, but you must think about these questions now. We're still in the requirements gathering phase, but we're thinking about questions that we need to have answered for when we get to these stages, because they have an impact on the requirements of the design that we're trying to put together now, high quality, solid requirements to have a design later. So I want to make that clear. So how do you verify that the final system satisfies each system requirement? When you eventually have a final build, how do you make sure that you satisfy the mandatory requirements? And since you're probably going to be looking at trade-offs, some more narrow than others, how well it satisfies the trade-off requirements. You want to make sure that if you make trade-offs, that you are really getting what you were going to get for that compromise, that it was for not, that it wasn't for not. So these are all very important questions that go to the heart of the quality of the requirements gathering process. And notice that they are all open-ended questions. There are no yes, no. You want to avoid yes, no questions. Because you don't get, by definition, if you're dealing with a complex system, is a bunch of gray area to begin with. And you want to make sure that you get clarity by soliciting a specific input, but in a way that you're getting information. And yes, no is too, it just takes you to one extreme or the other, but it doesn't allow you to get that clarity and that insight. So all these questions are open-ended. One important part of any design and development endeavor is reevaluation. You want to reflect so you can learn and feed forward lessons learned to the next project. So you want to also think about that. And we're going here through these questions that are of a very general nature, so you at some point may have to do the hard work of applying that to a specific project. That's actually a challenge, but there are a zillion of projects, so I cannot just pick one, because then it may shortchange the overall philosophy. So I'm giving you the general case, but you may, as an example that is specific, you may build in into your product a way to gather activity, such as a log of activity, for example. And that log may be used as part of the reevaluation. You may be logging information to see how your system is performing, and that may feed and be part of the reevaluation exercise later on. But you have to think about that now, because if you are going to put in the specification the necessity to keep a log, a performance log, then that needs to be put in now, if that's the process. And you may even think about what are specific activities that warrant someone to be a person that is going to do a specific job beyond the obvious. We're not talking about the obvious, but beyond the obvious. So these are important questions, and you can use them. They're available to you to use as a starting point of a questionnaire with your team in this thought exercise as you are trying to gather good requirements. As I mentioned yesterday, the main benefit of going through this exercises is to reduce risk. The risk of execution in maximizing the likelihood that you're going to have a product on time and on budget. So you can imagine that all this gathering is going to generate a lot of documentation and data. So A main benefit of the tools that I mentioned, systems engineering tools, software tools, like the ones that I mentioned, is that they get away from being document-centric and focusing on this knowledge building as you go through the project as a database. That's a different view, because it's very different if you are document-centric. There's going to be duplication. There's going to be duplication across documents, and there is going also to be a burden to keep documents up to date. So usually what happens is that documents become stale, and there is a lot of enthusiasm at the beginning, but then they are not maintained. So that's a difficulty, that if you look at the generation of all this data as a database issue where you can actually extract different views for different users, all the data is there. All you have to do is present it in different manners. Then everybody's working off a common database, and you're always just updating a common single database. So that's a data-centric approach. So normally, if you had a document-centric approach, you would think of, okay, we have specifications, interface requirements, system design, analysis and trade-off, test plan, so very sequential in nature. But the data-centric approach tries to look at it from a different perspective. So you don't have all these documents, because there will be overlap among these documents, so keeping them coherent is a real challenge. So this is basically what I just said. So let me go through the next slide. And this is where we're going to stop today, and next Monday we're going to start discussing software engineering. Okay? Thank you very much.